Hello, welcome back. So in this session, let's talk about arithmetic operations on bits. Everything we do right now is about bits, zeros and ones, zeros and ones. So when we do some arithmetic operations like addition, subtraction, how do we do that um, how do we perform these operations on bits? So without wasting time, let's dive into it. Now, arithmetic operations on bits involve performing fundamental math operations like addition, subtraction, multiplication, and division. Most especially, what we are doing, we are performing these operations on binaries, not on decimals, okay? So we are performing it on base 2, not on base 10. We are used to doing addition on base 10, 10 plus 10, 2 plus 2, 3 plus 5, 7. Those are decimal base 10 representation. But what we are going to be talking about in this session is performing arithmetic operations on base, base 2. All right. So these operations are the core of all digital computing. Okay, as computers operate using binary, we all know this. All right, everything that we do in computer here has to do with this binary logic, zeros and ones. So every operation we're performing is only going to be on zeros and ones. So now, but basically, we might not be looking at the multiplication and division. All right, definitely you can do multiplication and division on binaries, but when it comes to the computer, all right, the computer does not actually have any uh, logic gate for performing multiplication and division. So we're not going to be talking about that in this session. There will be no need, okay? So there's a way computer actually does multiplication and division. Basically, it is using the addition and the subtraction. So um, we will be leaving multiplication and division out on this session. So what are the practical uses of these arithmetic operations? Embedded systems. We use these arithmetic operations on embedded systems. Okay, if you don't know what embedded system is, embedded systems are computers that are inside some of the electronics, maybe your television, your washing machine. All right, these are computers that are embedded, so we don't see them. They are embedded inside electronics. Okay, so they actually perform bit level maths. Okay, cryptography. All right, cryptography uses bit level operations. So some of you that would want to go into blockchain, all right, what's the name again? Cybersecurity. All right. These are going to be very, very useful. Okay, because they use cryptography uses bit level operations. So there is something we call bit level, bitwise operations in some programming languages. When I started learning, I didn't, it was so scary for me, but it's not going to be the case for you because we are going to be explaining it short. In the next section, we'll be talking about bitwise operation or something we call logical operations. Here we'll be talking about arithmetic operations. So in the next session, we'll be talking about logical operations and they will be mentioning bitwise operations, okay? So in digital signal processing, okay, it is a efficient math at bit level. So these are the places the arithmetic operations actually are performed. But it's okay if you don't understand any of this, okay? But don't worry, when you now get to maybe any of this, maybe game development, optimize performance through shift and bitwise operation. So when it comes to game development, for the people who would want to go into game development, you would actually be doing something we call bitwise operations. So you need to understand how these things work, how these operations on bits work. All right. So now let's go into binary addition. How do we perform addition? The normal way we perform addition in decimal, that is the normal way we do it here. Okay. So now let's take a look at this is the binary representation of 13, 1101 plus 1011. All right. Now, let me bring up my board. Okay. So if I want to, if I want to perform 13 plus, I'll have to check and look back at what do we have there. We have 13 plus 11. So if I want to do 13 plus 11, all right, this is how we do it normally in decimal. I will have 13. All right, and I will have 11. So if I want to do this addition, of course, I will do 3 plus, of course, this is addition. I'll say 3 plus 1, this will be 4, and 1 plus 1 will be 2. All right? So if I want to do maybe 17 plus 14, remember the carries, all right? 7 plus 4 will give us 11. Of course, we can only represent from 0 to 9. That means there is a carry. So 7 plus 11 will give us 14. So we'll now say 14 divided by 10, because 10 is the base, you understand? So we say 14, since we cannot represent 14, there is no digit, there is no single digit for 14. We can only represent from 0 to 9. So we say 7 plus 4 is 11, sorry. So 11 divided by 10 is what? It is 1. It will give us 1 remainder, 1. So we will write the remainder here and carry the 1. All right. And now add it to this one. That 1 will be 10. Do you understand? So that this one that we are carrying, all right, we'll call it 10. Then 10 plus 1 will give us 11. Do you understand? All right. So 7 plus 4 will give us 1. Then 1. Then that 1 will add it to this 1. That will be 2. So 2 plus 1 will give us 3. All right. So this will give us 31. So 7 plus 7 plus 4 will give us 11. So we'll now say 11 divided by 10, which is the base, will give us 1 remainder 1. So we'll put the remainder here and carry the 1. Add it to this one. This will now give us 2. All right. So 2 plus 1 will give us 3. Now, if we want to do addition in binary, you say 1101 and 1011. So this is 13. So if you want to do this addition, we are going to say, I will have to erase. So we are going to, it's almost the same thing like the decimal. All right. It's 1, 1, 0, 1, which is 13. Let me bring the other one. 1101, 1011. This is 11. All right. So 1101, oops, 1011, right? 1011. Okay. So now 1011. All right. So this is equivalent of 13 in decimal, and this is 11. So here we are doing addition. All right. So we are going to add, I'm differentiating. All right. Maybe. Okay. Sorry. Let me use another color. Okay. So let me just delete this. This is 0, 1. This is 0, 1. And this is 1, 1. All right. So I'll just use another color to, all right. Okay. All right. So now what are we going to do? We will say 1 plus 1 is what? Will give us 2. Now remember that the maximum number we can represent in binary is 1. You know, it can only be 0 and 1. So 1 plus 1, all right, let me change my color. 1 plus 1 will give us 2. That means we cannot represent 2, just like we cannot represent anything above 10. So 1 plus 1 will give us 2. Then what we are going to do, we are now say 2 divided by 2 will give us 1 remainder 0. Do you understand? Just like we did in the other one. 1 plus 1 will give us 2. And we cannot, because we can only represent zeros and ones in binary. So we will now say that's 2 divided by 2, because 2 is the base. 2 divided by 2 will give us 1 remainder 0. So we'll write the remainder here, which is 0, and we'll carry the quotient. We'll now take this one and put it here. All right. So 1 plus 0 will give us 1. Then we'll now do, this is now 1 now. So 1 plus 1 would also give us another 2. Then we'll now do 2 divided by 2 will give us 0, remainder 1. So we'll write the 0. All right. Carry the 1, add it here. 1 plus 1 will give us 2 here. So 2 plus 0 will now give us 2. All right. Then 2 divided by 2 will give us 0, remainder 1. Then we'll carry that one, add it here. It will now be 2. 1 plus 1 is 2. Then this 2 will now have 2 here. The 2 plus 1 will now give us 3. Do you understand? It will give us 3. So 3 divided by 2 will give us 1 remainder 1. So we'll add the remainder here, and then there is an overflow now. Don't worry, we'll talk about overflow. So there is that we are having another 1 remaining. All right? So you can see. All right? I hope you understand what I'm doing here. 1 plus 1 will give us 2. All right? So we cannot represent 2. We cannot represent 0 and 1. So we now say 2 divided by 2 because the base here, we are working with base 2 here. All right? So 2 divided by 2 will give us 0. Will give us 1 remainder 0. So we'll add the 0. We'll put the 0 here. Take the 1. That 1 will add it here. 1 plus 0 is 1. 1 plus 1 is 2. Then 2 divided by 2 will give us 1 remainder 0. So we'll write the remainder, take the quotient, which is 1. That 1 will add it to this one. 1 plus 1 will give us 2. 2 plus 0 will give us 2. We'll do 2 divided by 2 again will give us 0 remainder 1. Sorry, 1 remainder 0. We'll take that 1. Add it to this other one. That will be 2. 2 plus 1 is 3. Then 3 divided by 2 will give us 1 remainder 1. All right? But right now, there is an overflow. All right? So we'll talk about what overflow really means. Okay? In this session, we'll talk about overflow. But the thing is this. It means that we have 4 bits here. All right? And we have 4 bits. And our result is 5 bits. Remember, when we were talking about this bits thing, I mentioned that here we are using 4 liters of fuel to go and get 5 liters of fuel. So it means that we will need to represent the result. 13 plus 11 will give us 24, right? All right. And if you check, 4 bits, all right, will take 2 raised to power 4, all right? It will take it will represent 2 raised to power 4 if it is unsigned. All right, if it's unsigned, it will be 2 raised to power 4. 2 raised to power 4 will give us 16. That means 4 bits can only represent the maximum of 0 to 15. All right, I mentioned this thing in the previous session. So now we are using our result is 24, and we cannot use 4 bits to represent 24. All right, what we can use to represent 24 is 5 bits. And then that is why we are having an extra bit here. All right, so this is what we call overflow. All right, we'll talk about overflow in the next in this session. We'll talk about overflow. So we are adding 4 bits plus 4 bits, giving us more than 5, is giving us 5 bits. So, but basically we have added. So we now have 24 here because 1, 1, 0, 0, 0 is 24. All right, so but this is how we do it. So now you can see we have 1, 1, 0, 0, 0. Okay, so but don't worry, we'll talk about this extra bit that came in. We are using 4 bits here, but we now have 5 bits here. So we'll talk about this overflow. All right, now the carry is handled similarly to decimal. All right, just like we have shown you how the carry is being handled. Okay, so adding the same number is the same as shifting the bits to the left. Now let me show you something. When you're adding the same number, all right, when you're adding this, if you have any question, please always reach out. Always reach out. All right, always reach out if you're having any question. Okay, so when you have the same number, let's assume I have 5. 0, 1, 0, 1. Now this is 5. I believe so. Yeah, this is 5. All right. So if I want to add 5 plus 5, if I want to do 5 plus 5, is the same as this is 5 plus this is 1, 0, 0. So if I want to do 5 plus 5, because both of them are the same number, I just want to show you a trick. If we do this, 1 plus 1 will give us 2. 2 divided by 2 will give us 1 remainder 0. So we'll write the remainder here and carry that 1. So 1 plus 0 will give us what? 1. 1 plus 0, this 1 plus this 0, all right, will give us 1. Then this 1 plus this 0 will not give us 1. All right. So there is no remainder, there is no quotient. So there is no overflow, there is no carry here. So 1 plus 1 will give us 2. 2 divided by 0 will give us 1 remainder 0. So we write the remainder and carry the 1. That one will put it here. So 1 plus 0 will give us 1. Then 1 plus 1 will give us 1. So this is now 10. All right. This is 10. But I said that if you're adding the same number, which is 5 plus 5, all right, all you have to do is to shift the bits. Now, if you can see, what we just did was 101, 101. Look at this 101, all right, that we have here is what we are having here. So we can just shift the bit. So if I say, if I have 0, 1, 0, 1, and I have another, I want to do this number, I want to add it to itself. All I can do is to shift the bit by doing what? I can shift the bit to the left. Okay, so what I will do is I will add 0, all right? Then I will take this 1, I will take this 0, and I will take this 1. So I have shifted it now. I will abandon this 1. So you can see that I have shifted the bit to the left, and then I have 1010, which is the same thing here. So if I have something like um um zero, if I sorry, if I have something like if I have something like 0 0 1 0. Now this is 2. All right, this is decimal binary for 2. Now, if I want to say 2 plus 2, I don't have to go to do all these things. No, I don't have to do all these things. I can just shift the bit. Do you understand? I would add, first of all, if I want to do it, what I would do is I'll add 1, I'll add 0 here. Then I would bring this 0, this one. I'll bring this 0 here. I'll bring this 1 here, and I'll bring this 0 here. Sorry, this is 0, this is not 1. And then I will leave this one out. Do you understand? I have shifted the bit to the left. So what I did was this, I will add a 0 before taking these other ones. So I have 0, 1, 0, 0. So what I did was I added a 0 first, then I started taking the first 0, 1, and 0. Then I'll throw away this other one. So this is like shifting the bit. So if you check this thing now, this is 4. This is the binary representation of 4. So if I want to try something like 3, I will say 0, I will say 0, 0, 1, 0. No, this is 5. If I want to do something like 3, 3 is binary representation for 3 is 0, 1, 1. Okay? So this is the binary representation of 3 in 4 bits. So if I want to do 3 plus 3, I don't have to go and do all these things I did here. I will just have to shift the bit. So how do you shift the bit? First of all, I would just add a 0. All right. Then I will now start adding this one. So this one will come here, 1. This one will come here, 1. And this one will come here. This 0 will come here. So I now have 0, 1, 1, 0. And if you check this thing out, this is 6. So this is what we mean by shifting the bit. But if this is confusing, please don't mind. Go on with this one. All right. Go on with the other way. So there are 2 ways you can actually do this. If you want to add 2 numbers, you can shift the bit to the left, or you can actually do the normal addition. Okay. All right. So if you get confused, please, you can also ask questions. All right. We're always available in case you get confused about any of this. While you're taking your class, just be writing down your questions. Okay. Now we also have binary subtraction. It uses the normal borrow, all right? So when we have, this is binary representation for 10, all right? So if you do this, 10 minus 3 will give us 7. So now, but before we do this, let me remind us of how we do subtraction in decimal. All right, so let's say I have I have 16, all right, minus 9, all right? So here now, 6 minus 9, 6 is less than 9, so it will not go, remember. Then I will borrow 1 from here and add, that 1 will be 10. That 10 plus 6 will be 16. So 16 minus 9 will now give us 7, all right? And then this will not be 0 because I have borrowed 1 from here. It will not be 0. So this will be 7, all right? This will be 7. Now I can also have something like 24 minus 8. All right. If I go on now, 4 minus 8, it will not go because 4 is less than 8. So I will borrow 1 here. This one will become 10 because we are working in decimal in base 10. So this 10 plus 4 will now be 14. 14 minus 8 will give us 6. Then this 2 now will remain 1 because we just borrowed 1 from it. So this will now be 1 and we'll bring down this 1. So it will now be 16. So this is how we do binary. This is how we do decimal subtraction. So what of binary subtraction? How do we do it? Okay, this is how we do it. So let's say I have 3. I want to do 3 minus 2. And remember, this is 1 0 0 0 1 1. This is 3 in decimal. This is 3. And then I want to do 2. I want to do 3 minus 2. I will say 0 0 1 1. Sorry, it is too close. Let me erase it. They are too close to each other. All right. So I will say 3 is 0 0 1 1. And 2 is 0 0 1 0. So this is actually 2. So if I want to say 3 minus 2, how do we go about it? All right. First of all, we'll do the way we do, just like the way we did in decimal. 1 minus 0 is very possible because 1 is greater than 0. So 1 minus 0 will give us 1. 1 minus 0 will give us 1. 1 minus 1 will give us what? 0. All right. And then 0 minus 0 will give us 0. And 0 minus 0 will give us 0. So what do we have here? We have what? We have, this is 1. This is the binary representation of 1. All right. So 1 minus 0 will give us 1. 1 minus 1 will give us 0. 0 minus 0 will give us 0. 0 minus 0 will give us 0. So let's do something different. Let's do 5 minus. Let's do 5 minus 2. Let's do 5 minus 2. So 5 is 0 1 0 1. Now this is binary representation of 5. And 2 is 0 0 1 1. No, this is 3. Sorry, this is 3. But we can do, okay, here we are doing 5 minus 3. Okay, so 1 minus 1 will give us what? 1. Will give us 0. 0 minus 1, it will not go because 0 is less than 1. So what do? We'll borrow 1 from here. All right, add it to this place. Do you understand? It will not be 2. All right, so 2 minus 1 will give us 1. Okay, and then this will not be 0 because we just borrowed 1. Remember, in base 10, when you borrow 1, that 1 will be 10. Then 10 plus that number will give you whatever you want to give you. But here, if you borrow any number, it will be base 2. It will be 2. So we borrowed 1 from here and added it to this 0, which is 2 plus 0 will give us 2. 2 minus 1 will give us 1. Then this is now 0 because we have borrowed this 1. 0 minus 0 will give us 0. And 0 minus 0 will give us 0. And if you check where, this is the equivalent of 2. So 5 minus 3 will give us 2. Do you understand? So this is 2. So try out your own. Okay, let me recap again. 1 minus 1 will give us 0. 0 minus 1 will not work because 0 is less than 1. So we'll have to borrow. We'll borrow 1 from here, all right? And once we borrow this one from here, this one will not remain 0. So we'll borrow this one. And this our borrow, one, the equivalent of it is 2 because we are working in base 2. So 2 plus 0 will give us 2. Then 2 minus 1 will give us 1. Then this one is now 0. 0 minus 0 will be 0. 0 minus 0 will be 0. So that's how we got here, all right? Okay, so there is also something now. The thing is that computers actually make use of the best, the easiest, the most efficient way to do anything. In subtraction of 2's complement by logic gates works differently. All right, it works differently. So I hope this is not going to confuse you, but this is how it works. Okay, let me show you. When working with 2's complement, this is also perfect. This is perfect, but this is how the computer actually computes it. When you have, when you want to do, when you want to do, when you want to do 5 minus 3, all right? This is what the computer will do. Computer will do 5, all right, plus minus 3. They are still the same thing. Do you understand? They are still the same thing. But with this way now, it will be easier for the computer. Now, computer does not need to have an adder. Okay, don't worry, we'll talk about logic gates, okay? But logic gates are the things that actually perform these operations for us. So computer, the engineers, they don't need to create a different logic gate or a different device that will do addition and another one that will do subtraction. Because if you watch this thing now, and a device that will do addition can even do subtraction. Now, how can a device that does addition do subtraction? Is by saying, instead of 5 minus 3, it will now say 5 plus minus 3, because this is the same thing. Both of them are the same thing. So there will be no need to create a device that will do addition and another device that will do subtraction. So the device that does addition is actually called adder, an adder. We'll talk about that in later sessions. But now we just one device, they can do the same thing. So what you have to do here is this. 5 plus minus 3 is the same thing with 5 minus 3. It's the same thing. So what they will do is this. First of all, you will have to get the negative. You will have to get the negative of 3. All right. Then you now do 5 plus that value. So remember, this is 3. This is the value for 3. 0, 0, 1, 1. So remember the 2's complement. If you want to, this is positive 3. All right. So remember in our previous sessions, if you want to convert this number now to its negative, using the 2's complement, because remember, whatever we are doing, data representation, integer representation, is we are using the 2's complement. I mentioned this in the last session. So if you want to convert this now to its negative value in 2's complement, what you have to do is, first of all, you flip the whole bits. So you flip, this will now be 1, 1, 0, 0. Then you will now add plus 1, which is 0, 0, 0, 1. So you will do this plus. Remember, we talked about the 1's complement and the 2's complement, okay? So when you do this, 0 plus 1 will give us 1. This will give us 0. This will give us 1. And this will give us 1. So this is minus 3. This value is minus 3. So we have converted this plus 3 to minus 3 using the 2's complement. Remember, this is the positive 3. So we'll flip the bits, then we'll add 1 to it. And this is what we get. We now get minus 3. So now what we are now going to do is that instead of saying 5 minus 3, all right, we are now going to say 5 plus this value. This is the minus 3. So we'll now say 5 is 0, 1, 0, 1. Then minus 3 is 1, 1, 0, 1. All right. So here we are not doing addition instead of doing subtraction. All right. So both of them, you can do this, but for the sake of devices, there will be no need to be creating different devices. One device can actually do this. All right. So we'll now do 1 plus 1 will give us 2. So 2 divided by 2 will give us 1 remainder, 0. We'll write the remainder, take the carry and put it here. 1 plus 0 will be 1. 1 plus 0 will give us 1 here. The same thing goes here. All right. Yeah, something 1 plus 1 will give us 2. 2 divided by 0 will give us 2, 1 remainder. 0, we'll take that 1, put it here. This 0 will not be 1. 1 plus 1 will give us 0 and 1. All right. So now 5 plus 5 minus 3 will now there's something we'll call that we will have to take this one out. Then this is the remainder. This is the value, which is 2. Okay. Don't worry, you're going to understand why we have to discard this value. All right. That's why we have to discard it. But now this is 5. This is minus 3. 5 plus minus 3 will give us 2. So this is 2. All right. Okay. So let's continue. There's something we also have to understand: overflow and underflow. All right. Now, when you go to the filling station with 4 liters of fuel and you now go there, they will now, instead of 4 liters, they will add 5 liters. There will be an overflow. As simple as that. That's what it means. So when you're adding 2 numbers or even subtracting 2 numbers, if you're adding 2 numbers, you're adding 2 numbers, 4 bits, 2 numbers, and then their result became a 5-bit integer. That means there's an overflow. All right. So the computer handles it differently. We also have underflow. Some numbers will be like have a negative value. All right. And if you actually have a number that is less than what they can actually carry, all right, there will be an underflow. So let's go and understand better. Overflow occurs when the result of a binary arithmetic operation exceeds the range that can be represented with the available number of bits. All right. When you have 4 bits, and when you do the addition, all right, you will not get something like 5 bits. You saw me when I was doing that addition. We actually got, when we did um, 11 plus 13, we actually got 24, and we needed 5 bits to represent the 24. So that is an overflow. All right. So that means you would have to, you need to, when you're representing that data, especially when you're programming, all right, most of the programming languages actually handle these things for you. All right. Sometimes when you try to do something that is bigger than, when the result is going to be bigger than the number of bits, the system handles it for you. So in unsigned arithmetic, overflow will wraps around to 0. If there is an overflow, all right, in unsigned arithmetic, remember, unsigned arithmetic means that we are performing arithmetic operation on unsigned integers. So in signed integers, especially the 2's complement, overflow can cause a positive to become negative or vice versa. So for the unsigned arithmetic, overflow will make the whole number to round up to 0 if there is an overflow. But in the signed arithmetic, overflow can cause the positive number to become negative or vice versa. So what is underflow? Underflow happens when a subtraction result is less than the minimum value that can be represented. If you say 0 minus 1, all right? If you say 0 minus 1, it is going to be underflow. So in an unsigned binary, this leads to wrap around to a large number. It will just be weird, okay? So in signed binary, underflow is just a type of overflow when you go below the smallest possible signed value. So let me show you what I mean here. Let me show you what I mean by overflow, okay? So now, let me erase everything here. Let's say normally we can actually use 2 bits to represent, this is 2. This is the value for, this is binary representation of 2, and this is binary representation of 3. Here we are using 2 bits. And if we say 2 plus 3 will give us 5, you know that. But the thing is that 5 cannot be represented with 2 bits, so there will be an overflow. So if I go on now, all right, if I say 0 plus 1 will give us 1, all right, then 1 plus 1 will give us 2, which is 2 divided by 2 will give us, remainder will be 0, and we'll carry over the 1. You can see now there is an overflow. It means that the result of this arithmetic, there will be an overflow because the result, which is 5, will need more than the number of bits here. Okay, I know this might be hard to understand, but just grab it. On overflow means that here we are using two bits to represent. This is the simplest example that just comes to my head. All right, here we are using two bits to represent. This is 2 and this is 3. Okay, so this is 3. All right, then but this is 5. So here we are using 3 bits. 5 will require at least 3 bits to represent it. Meanwhile, the result, we are using 2 bits to say them. So in the programming language, there'll be an overflow. And when there's an overflow, if this kind of thing happens, all right, for unsigned integers, it will be wrapped to be 0. Okay? For negative, for unsigned integers, it might turn it to be a negative number or a positive number. So there is always a problem with this. Okay? So underflow means that, okay, some numbers can go, let's say 8-bit integer can go from -28 to +27. So if you do any arithmetic operation and it results to -129, that means that 8 bits can no longer hold it. It will need more than 8 bits to hold that -129. So an overflow is you giving a container more than what it can take, and an underflow is giving a container less than what it can take. Do you understand? So that is the best way I can actually explain this now. So let's take a look at some examples. When you have an unsigned overflow, here we have this 1 is 255 in unsigned integer. When you add 1 to it, there will be an overflow because 8 bits can only take from 0 to 255, if you remember. All right, 8 bits can only take from 0 to 255. So you cannot store 255 plus 1 will be 256. That means 8 bits can no longer take it because it is 256. It is beyond what it can take. So there will be an overflow. So, and once there's an overflow, the computer would round it up to 0. Instead of giving you 256, the computer will round it up to 0. That means, but the thing is that most programming languages protect us from this, but this is called an overflow. 8-bit, all right, can only take from 0 to 255 for the unsigned. But here we are not doing 256, which it cannot take. It's an overflow. Now, it wraps around and it wraps it to be 0, and there is an overflow. For unsigned underflow, 8 bits can only take -128. But if you say 0 minus 1, all right, it will give us plus 255. All right, 0 minus 1 will give us plus 255 because if you actually do this 0 minus 1, if you can go ahead and do 0 minus 1, all right, this is what it's going to give you, but it's an underflow, and it wraps around to maximum value, which is underflow. So if you say 0, if we do something like this, let me go to the board. Okay, if you do something like this, if you do 8 bits, 0, 1, this is 3, 4, 5, 6, 7, 8. Now this is 0. Now 1 is 0, 0, 0, 0, 0, 0, 0, 1. Okay? If you now do minus, all right, it's not even going to work. You understand? Okay, because there is going to be an overflow. Now, if you say, okay, we want to do 0 minus 1, now where are we going to do the borrow? Where are we going to do the borrow? Because we need to borrow. Unless we now say, okay, if we convert this, it will not be 1. It's not going, there will be an underflow. All right, there will be an underflow. So it will result to underflow, and we will not get this, which is not intended result. But the thing is this, you have to watch this. All right, you have to be careful of underflow and you have to be careful of overflow, because the system will just give you, the system will even be confused because it cannot take it. And most times when you're writing a program, they will throw an error. The programming language will throw an error. Okay, so for sign overflow, when you say 1 plus 127 plus 1 will give you 128. 8 bits can only take, signed 8 bits can only take from minus 128 to plus 127. So you cannot store 120 plus positive 128. You cannot store it. So you can see that it gave us something different. All right. So it cannot store it. So there will be an overflow here. So the sign flips, which is an overflow, and then for sign underflow, it would give you a wrong sign. So be careful of overflow and be careful of underflow, all right, for both. So what it means is that you are trying to use a smaller size bit, a smaller number of bits to represent a value that is more than what that number of bits can actually take. Okay, so the last thing we'll talk about is sign extension. All right, sign extension is the process of increasing the number of bits of a signed binary number while preserving its value and sign, whether it is positive or negative. So this is what we mean. It is commonly used when converting a smaller signed number to a larger one. Let me show you what we mean by sign extension. So now, if you have 4-bit integer 0, 0, 1, 1. Now it is 4 bits, but if you want to extend it to 8 bits, what would you do? You need to extend it, and while you're extending it, you need to preserve the sign. Remember, if it is remember now, when this is a signed integer, remember that we use the most significant bit to represent the sign. So that means this is a positive number, remember? All right. Now, so if you want to extend this thing and you also want to maintain its sign, all you have to do is you will pad it, you will pad, you want to extend it to 8 bit, you will pad it with all zeros, because this will preserve the sign. So this is what we mean by sign extension. This is a positive number, 4 bits. The most significant bit is 0, and this is positive. So you cannot come and add 1, 1, 1, 1. No, because it will change the value. Now, if you have something like this, 1, 0, 1, 1, for signed integer, remember, because the most significant bit is 1, which means it is negative. All right. If you want to extend it, if you want to sign extend it, instead of, you cannot use 0, because if you use 0, it means that the most significant bit will not be plus, and then it will change the value. So you have to sign extend it using 1. So 1, 2, 3, 4. So this is now 8 bits. So I've extended this one from 4 bits to 8 bits. All right. And I've extended this one from 4 bits to 8 bits. So you have to watch the sign. When you want to do sign extension, you have to watch the sign. So if that number starts with 0, all you have to do is to extend it with all zeros. If it starts with 1, all you have to do is to extend it with all ones. Okay. So if we go back to our slide now, it is used by, if you want to convert a smaller signed number to a larger one, I just converted 4 digits to 8 digits. So I have signed extended. Here I also signed extend this one to 8 bits. So it is used when you want to convert a smaller signed number to a larger one, from 8 bits to 16 bits, or from 4 bits to 8 bits. It's also used when you're performing arithmetic between numbers of different bit sizes. So let's assume we have something like this now. So let's assume we want to do arithmetic of 2 numbers. One of them is 4 bits, 1, 0, 0, 1, and the other one is 8 bits, 0, 1, 1, 0, 1, 0, 1, 1. Now, there is no way this is 8 bits and this is 4 bits. If I want to perform an arithmetic addition, the arithmetic operation here, I will have to extend this one to 8 bits so that they can match. All right? So that they can match. So if I want to do this, I will have to extend this one. So if I want to extend this one, first of all, you will check the most significant bit, which is 1. That means this is a negative number. So to preserve the sign, you extend it with 1, 1, 1. All right. So this is, I've extend this thing now to 8 bits, so that now I can now do the arithmetic operation now. So if you have two numbers, one of them, they have two different bit sizes, you can extend them to actually get the same number of bits. Okay. So why is sign extension important? When dealing with signed binary numbers in 2's complement form, we must copy the sign bit. So you're not going to throw away the sign. Remember, when you're working with signed binary numbers in 2's complement, the most significant bit is the sign bit. And once you change that sign bit, it would have a different value. So we have to preserve it, okay? So if the most significant value, which is the sign bit, if it is 0, the number is positive, then you have to extend it with zeros. If the most significant bit is 1, that means that number is negative. You have to extend it with all ones. That's what I just did now, all right? So I've just shown you an example. So look at this one now. This is 13, all right? And if you want to extend it to 16, this is 8 bits, all right? If you want to extend it to 16 bit, you first of all check the most significant bit, which is 0. That means this is a positive number, all right? So if I want to extend it, I will add all zeros. I will add extra 8 zeros to this one. This is extending it to 16 bit, all right? So for sign bit is 0, so we extend with zeros. So this is 8 bits. And then if I want to extend it to 16 bit, I will add all zeros because it's a positive number and the most significant bit is 0. So I have to maintain that sign bit. So another one is for negative numbers. Now this is for 13, negative 13. It starts with 1. The most significant bit is 1. That means if I want to extend it to 16 bit, I will maintain that sign bit by adding ones all through. All right. So this is how it works. So why can't we just pad with zeros? You cannot just pad with zeros because if you pad with zeros, it will give it a meaning. Now we have positive ones here. This is a negative number because this most significant bit is 1. If you go and pad with zeros, it will give it a different number altogether. Do you understand? Remember, any number that starts for the signed integers, any number that starts with 1 is a positive number. So when you go and pad with zeros, that means you have changed this value. It's no longer going to be minus 13. It has now turned to plus 253. So be careful. So this alters the meaning completely, turning minus 13 into plus 243. So just be careful. If you want to sign extend, watch the most significant bit. If it is the most significant bit is 1, add ones all true. If the most significant bit is 0, you add zeros all true. All right. So it is used in arithmetic. Okay. And I've just shown you all this. Okay. So you extend it. All right. So this is how it works. Okay. So thank you very much. Please, if you get any confusion, please reach out to us. We expect that. So if you got any confusion, reach out to us so we can explain better to you. Okay. Thank you very much, and I'll see you in the next session.